Why do the rider's distances from the pivot affect the seesaw's responsiveness? The answer to that question is that the farther the rider's masses are from the pivot, the greater the seesaw's overall rotational mass, and the slower its angular accelerations. Two riders can balance the seesaw in a variety of ways. To begin with, they can go to the ends of the board and adjust their distances from the pivot carefully until it balances, that is, until it experiences zero overall torque due to gravity. I'm pretty much there. Balanced seesaw. But they can also come in close to the pivot and sit like this with much smaller lever arms to work with now so that they're producing much smaller torques as individuals. But once again, those two torques sum to zero, and there's zero overall torque due to gravity on this seesaw. So there are a variety of ways to balance the seesaw, and you might think that there's no significant difference between those choices. But that's not true. There is a significant difference. The farther these two riders sit from that central pivot, and therefore the axis of rotation, the greater the seesaw's overall rotational mass. Now, rotational mass is not something completely independent of ordinary mass. They're related, just as forces and torques are related. Every portion of the seesaw's ordinary mass contributes to the seesaw's rotational mass, and the amount of that contribution depends on where the portion of ordinary mass is. More specifically, on how far that portion of ordinary mass is from the axis of rotation. And that dependence on axis of rotation is a strong one. Small, modest changes in distance from the axis of rotation can lead to large changes in the rotational mass contribution. The amount of rotational mass contributed by a portion of ordinary mass is equal to the ordinary mass itself times the square of the distance between that portion of ordinary mass and the axis of rotation. So taking a small portion here and doubling its distance from the axis of rotation doesn't just double its contribution to the rotational mass, it quadruples it. That means that for the riders, when they sit in close and their distance from that central pivot and center of rotation, axis of rotation, is small, they contribute very little to its rotational mass, or the overall rotational mass of the seesaw and riders. Even though these riders have large masses, they're too close to the axis of rotation to contribute very strongly to its rotational mass. But if they go out like this to large distance, well, then their contribution to rotational mass is huge. They might be only 10 times as far away from the pivot as before, from that axis of rotation. But an increase of distance by a factor of 10 is an increase in contribution to rotational mass of 10 times 10, or 10 squared, which is 100. So the rotational mass contribution of these riders could easily be 100 times that of these riders. It's a big effect. To see how big, I've made these two rods that look the same and have the same masses. They contain the same materials, actually. But the difference is that in one of these rods, the mass is all in the middle, near my hand, under my hand, hidden from view. And in the other bar, all of the mass is far from my hand, at the ends of the bar. So, same mass, but in this case, it's moved way out far from the center of rotation, which will be here in the middle of the bar. And the rotational mass of this bar is something like 30, 40 times that of this one. Big difference. To see that difference, since you can't hold the bars, let's go get some help. Annie and Megan are going to help me here with these two bars. Now, these bars have the same masses and the same weights. And you can check that out. Just compare the weights. Do they feel the same?
Yeah, definitely. Mm-hmm.
Yeah. So just by weighing them in your hands, you can't tell the difference between these two bars. But that doesn't mean they're identical. So the difference is going to be subtle, and this difference will show up maybe when you begin to try to rock them back and forth. So I want Annie, grab it in the middle of the bar. Megan, okay. Same thing. And I'm going to count to 3. And on the number 3, I want the two of you to rock it back and forth as fast as you can. That is, make it undergo angular acceleration first one way and then the other, back and forth as fast as you can.
Okay.
1, 2, 3.
Oh. This is really difficult.
So Annie's having no trouble here, and Megan's really lagging behind. Must be weak today, right? Yeah. Forgot to eat your breakfast. Okay, now swap bars.
Okay. Thank you.
And I'll count again. 1, 2, 3.
Oh.
Miraculous change. Something's different about these two bars. What do you think's different about the bars? They have the same mass. What's different? Megan?
Maybe the distribution of the mass within the bar.
So the distribution of the mass within the bar is different. Where's the mass in your bar right now?
In the center.
So your bar has almost all the mass in your hand.
Yeah.
As a result, the moment of inertia, or the rotational mass of this bar, is very small. It's very easy to make this bar undergo angular acceleration. How about yours, Annie? Where do you think the mass is located?
I mean, they must be at the ends, right?
Yeah, so all the mass in this bar is at the ends, where it contributes enormously to rotational mass. So they have the same mass, it's just distributed differently. In Annie's bar, it's at the ends. In Megan's bar, it's in the middle, and they behave totally differently when you try to rock them back and forth. Show us one more time.
Sure. I have to make a face.
Yeah, it's pretty dramatic difference. Unfortunately, you guys can't try it out, but if you ever come by, test out these bars and see how different they are.
Okay.
Thanks.
Cool, sure.
So you see, if you place an object's ordinary mass far from its axis of rotation, that object can have a surprisingly large rotational mass. Now, the distance involved here is between ordinary mass and the rotational axis. And you're often free to choose an object's rotational axis. If you do that, and if you change your choice, you may well change the object's rotational mass. That ability to change an object's rotational mass is why rotational motion is so complicated to calculate quantitatively. And that's a fact that keeps first-year physics graduate students rather busy. It's hard work. I want to give you a taste of the issues without trying to overwhelm you with them. But look at this rod. This is the rod that's very hard to wobble back and forth like this because it has an enormous rotational mass when you twist it back and forth about this axis, the one pointing toward you through my hand or away from you through my hand. About that axis, gigantic rotational mass. But what about this axis in which I'm twisting it back and forth like a drill or a screwdriver? It's easy. This direction, it has almost no rotational mass. That's because all the portions of ordinary mass are very close to the spindle-like axis about which I'm twisting it. So this rod here has two very different rotational masses. A huge one when you do this motion, and a tiny one when you do this motion. Now this is a fun and games rod, but something that you're more familiar with is perhaps a tennis racket. The tennis racket is a classic example of something that has three particularly important rotational masses. Its smallest rotational mass is for this rotation, about the top-bottom axis right now. This motion, most of the mass is pretty close to that axis, the spindle about which I'm twisting it, and therefore it has a relatively small rotational mass. The next larger rotational mass is for this motion, sometimes referred to as the frying pan motion when you're flipping pancakes. So this is the intermediate rotational mass. And the biggest rotational mass is for this rotation. In between these motions, life is extremely complicated, and it's beyond the scope of this class and something I don't like to deal with anymore. I've done it, been there, done that, I'll leave it. But these three distinct rotational masses, this small one, bigger one, biggest one, give the motion of a tennis racket or anything shaped like a tennis racket, the rotational motion is quite complicated. To make things even worse, these are all motions about the center of mass. These are all rotations in which the center of mass stays put. What if you shift the rotation so that you don't care about the center of mass of the tennis racket? For example, when you're swinging a tennis racket about your shoulder, in that case, you're shifting the mass of the tennis racket even farther from the center of rotation, the axis about which you're spinning it, and creating an even larger rotational mass for the tennis racket. So, the bottom line with all of this is rotational mass depends on your choice of axis of rotation. We're finally ready for the question I asked you to think about in the introduction to this episode. To remind you, that question asked, if you and a child half your height lean out over a swimming pool at the same angle and let go at the same moment, which of the two of you will hit the water first? Despite a fair amount of rotational physics under our belts, that remains a challenging question. So before I ask it and leave you free to answer it, I want to give you a little more background, get you all prepped for this question. First, what's the big picture issue? What is going to determine who hits first? It's going to be angular acceleration. The one of you that undergoes the fastest angular acceleration will develop the fastest angular velocity, will tip over the fastest, and will hit the water first. So look for big angular acceleration. Second, what is the axis of rotation about which the two of you are going to be rotating? It's not your centers of mass. It's going to be here at your feet. That leaves two more issues. One is the cause of angular acceleration, and the other is the resistance to angular acceleration. The cause is the net torque on you. The resistance is your rotational mass. And let's look at each one individually. First, torque. The torque is due to gravity. And to make our lives simple, let's compare the torques about your feet, that's the axis of rotation here, for you and the child. Now, I've made life very simple by using exactly the same board material. One is just half as long as the other. And this makes, this has all the physics in it, but none of the details. Life is easier. So you have twice the weight of the child, that's no surprise, and that weight effectively acts at your center of gravity, which is twice as far, it's right here in the middle, it's twice as far from the axis of rotation as for the child. So you're experiencing 4 times the gravitational torque of the child. You have twice the weight acting at twice the lever arm. 2 times 2 is 4. Right? 4 times the torque. That's the cause of angular acceleration. How about the resistance to angular acceleration? The rotational mass. Well, as compared to the child, who has half the mass here distributed around here, with the center of mass being about there, you have twice the mass distributed here and there. There's a center of mass here. The center of mass has moved out by a factor of 2. You have twice as much mass that is on average at twice the distance from the axis of rotation, namely your feet. Well, remember that the distance involved here in calculating the contribution of mass depends not on distance, but on distance squared. So the rotational mass that you have is 8 times that of the child. Twice as much mass at twice the distance, and you square the distance. So it's 2 times 2 times 2. That's 8. You have 8 times the rotational mass of the child. With that as background now, Answer the question. Which of the two of you tips over fastest and hits the water first? The child undergoes greater angular acceleration, develops a bigger angular velocity, and hits the water first. If you haven't already tried this experimentally, give it a go. All you need is 2 sticks, one twice as long as the other. I can show you what you'll see when you try it. Here's you, here's the child, and we'll put you both on your feet and tip you to the same angle, and then let go. 3, 2, 1. No question, the child reached the water first. It's a battle between torque and rotational mass. In both cases, about your feet. You have 4 times the gravitational torque acting on you as the child has. So there's 4 times as much twist trying to propel angular acceleration. But you have 8 times the rotational mass of the child resisting that angular acceleration. 4 times more impetus, 8 times more resistance. You get only half the angular acceleration of the child. So the child undergoes twice your angular acceleration and just goes through the whole rotational motion faster and wins the race to the water. Rotational motion clearly has some subtle complications, like a single object having more than one rotational mass, depending on your choice of axis of rotation. But let's leave all those complications for the experts. I chose seesaws as the topic for this episode because seesaws are comparatively simple. That pivot fixes the axis of rotation so that the seesaw can only rotate in one fashion. And in general, it only has one rotational mass. Things are simple. Nonetheless, the seesaw exhibits most of the issues of rotational motion, or at least the ones that I want to talk about and try to convey to you. I've already done that now. I've shown you most of what happens in a rotating system like a seesaw, with one important exception: energy. As the seesaw rotates, the riders are exchanging energy. And that is the topic for the next video.